This is SpaceTime, Series 28, Episode 132, for broadcast on the 10th of November 2025. Coming up on SpaceTime, Planet Earth's geology written in the stars, Taikonauts stranded in space following space junk impact, and the biggest supermoon of the year. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study has uncovered a striking link between the structure of our Milky Way galaxy and the evolution of planet Earth's crust. The findings, reported in the journal Physical Review Research, shows that crustal development was shaped not just by internal geological processes, but also by the impact of meteorites during Earth's journey through our galaxy. The Sun and its solar system are currently located in the Milky Way's Orion Arm, about 27,000 light-years from the galactic centre. The solar system orbits around the centre of the Milky Way roughly every 230 million years, travelling at an average speed of around 828,000 kilometres per hour. But the solar system's path through the galaxy isn't a perfect circle, and also it oscillates up and down through the galactic plane. The new research shows that the chemistry of tiny ancient crystals in Earth's crust may be capturing the rhythm of meteorite impacts during the solar system's passage through the Milky Way's vast spiral arms. The study's lead author, Chris Kirkland from Curtin University, says the work provides new evidence linking Earth's ancient geological record with the large-scale structure of the galaxy. Kirkland says tiny durable minerals called zircon crystals are providing a unique archive of Earth's interaction with the galaxy. By looking at chemical changes in these zircon crystals and then comparing them with maps of gas in the Milky Way, Kirkland and colleagues saw that the changes lined up with times when the solar system passed through the galaxy's different spiral arms, which are densely packed with stars and gas. Extra gravitational forces in these crowded regions may have disturbed icy comets at the edge of our solar system, knocking some onto paths that eventually sent them crashing into Earth. The resulting impacts have released enormous energy, melting parts of the planet's surface and producing more complex magmas, especially when interacting with water-rich environments. Kirkland says the findings open the door to a new frontier, one where geology can be directly connected with discoveries in astronomy. The research reveals that Earth's geological evolution cannot be understood in isolation from the broader galactic environment. He says it suggests that astrophysical processes on the galactic scale may have directly influenced the continents beneath our feet, and even the conditions that made life possible, in the process ushering in a new era of astrogeological science.
We have been obviously very fortunate in Western Australia to do a lot of analyses of rocks and specifically the crystal zircon, and we've created huge data sets, and those data sets have got patterns within them that tell us about the magmas within Earth and the diversity of magmas through time. And with those huge data sets, we were kind of interested in that pattern, and we discovered that that pattern actually matches an astrophysical pattern, and that's the pattern that we see from the solar system passing through the spiral arms of the Milky Way. And that pattern is defined by hydrogen gas, which creates a radio astronomy signal. And that radio astronomy signal seems to map quite closely into this geological signal, and that's really interesting, and we can think about potentially the reasons why there might be a connection between those two signals.
So what you're talking about is the galactic year. It happens as the Sun and solar system travel through the spiral arms, because we're in the Orion Arm now, but we're not just stuck in the Orion Arm. The Sun and solar system move through the various spiral arms?
Yeah, that's exactly right. So at the distance we are out from the central black hole within our Milky Way with its spiral arms, the solar system's going around at about 240 kilometers a second, but the density waves themselves at that distance rotate more slowly at about 200 to 210 kilometers a second. So that means that with given enough time, our solar system will migrate through those density wave arms, and that obviously then changes the galactic environment our solar system has seen. And then from that, we might think about our solar system passing through regions of higher dust density and gas density, and the knock-on implications of that may be recorded in Earth's geology, which I think is really fascinating to think about.
It's almost like a core sample of the galaxy, isn't it?
Yeah, that's why it's so, I think, exciting, right? Because astrophysics is great with these radio waves. It's how we understand our spiral arms of our galaxy, but we can't see through our central black hole, and we're within the galaxy itself. So making these maps of our galaxy, everyone's seen the artist renderings. We can't send a satellite out far enough to take a photograph back. So we use radio waves to create our understanding of the spiral arms of the galaxy, but we can't see through the central black hole. But we look far enough back in time, we could actually potentially use Earth's geology to help us understand what's on the far side of the central black hole.
And this is where zircon crystals come in.
Yeah, the geologist's best friend. They basically are this deep time archive of our planet. They crystallize, and when they crystallize, they trap a little bit of uranium, and that's important because over time that uranium changes to lead. So that means we've got this inbuilt stopwatch, this inbuilt clock in our zircon crystal. But not only that, the zircon crystals also contain other chemistry, other chemical information, and other isotopes we can use to tell us about a process. So that gives us information about time, but also our process. So then that gives us this really rich data set we can actually use to understand lots of things about our planet. And one of a beautiful example of that is the zircon crystals' oxygen isotopes tell us that we had oceans on our planet from very early on. But these oxygen isotopes also can tell us about where magmas are forming. Are they forming deep within Earth's crust, or are they forming near the surface? And what we find during these spiral arm periods is that there is more variability in our oxygen isotope signals. So it's telling us that magmas are forming in more wider range of places, deeper in the crust, but also shallower in the crust when we're passing through the spiral arms. And then we can think about, well, why is there a connection?
That's my next question. Why is there a connection?
Yeah, so I think we have to start thinking about impact playing a role. So that's the obvious reason to explain why there seems to be this correlation between our galactic spiral arms and the diversity of magmas on our planet. So one way of doing that is when we're entering the spiral arm regions, we're maybe dislodging more material from the distant icy regions of our solar system. That's known as the Oort cloud. So we might be disturbing material from there and sending in showers of comets and meteorites periodically into the inner solar system. And that's probably what's being, or at least it's a good explanation to explain why we're finding more diversity in crust-forming processes during these periods of time. So I think it's beautiful that we're potentially seeing now a connection between our planet and the wider cosmos when geologists frequently think about internal processes, and undoubtedly internal processes are important on our planet. External processes are also probably really important for our planet over its extreme duration of time. As I'm frequently reminded, correlation is not causation, which is true, but with larger data sets, we start to see patterns that we need to develop models to explain. And what I think is interesting, thinking about ways of testing this further. So you would predict that we should start to see similar patterns in lunar geology and Martian geology in terms of periods of impacting. So if that means more craters or a greater variety of geologic processes during those time periods, we're seeing an enhanced bombardment rate, or impact flux is the technical term. Basically, it just means more impacts during the periods that we're passing through the spiral arms of our galaxy.
And also, if places like Mars and the Moon don't have the plate tectonics that we have here on Earth, so that mixing doesn't go on.
Yeah, that's exactly right. So the record on Earth tends to self-erase because of plate tectonics and ocean crust being subducted. So that's why zircon crystals are so important, because they give us this deep time archive of our planet. But you're right. If we look at the Moon without plate tectonics, maybe it's of a complementary and supporting record. Of course, one of the issues with the Moon is that the impacts themselves, the craters self-erase. Your older craters are more likely to have been eroded by other craters coming over the top of them. So that's why the crystal record is actually really important, because it preserves with quite a lot of detail these processes that can be lost from other records.
Where would you like to see this go next?
I think we've been talking about it. I would love to have as rich deep time data set from Mars and the Moon to test this, and it's fundamentally important. What we're actually talking about is making a connection between our planet and how the crust of our planet came to be, which is important for life, and where we sit within the Milky Way. So it's really going from sitting on an analytical instrument, firing laser beams and looking at voltages and electrons, making correlations from that all the way up to the size of a craton, and Earth's crust, but then going right out to the huge scale of our solar system and then even bigger into spiral arms of our Milky Way. And that's kind of profound to be able to think across those different scales.
That's Professor Chris Kirkland from Curtin University. And this is SpaceTime. Still to come, Taikonauts stranded in orbit following space junk impact. And the biggest supermoon of the year. All that and more still to come on SpaceTime. Three Chinese Taikonauts are stranded in orbit after suspected space junk hit their Shenzhou 20 spacecraft just hours before it was slated to undock from China's Tiangong space station for the return journey to Earth. Mission managers are still assessing the damage in order to try and determine if it's safe for re-entry. If not, the trio will need to wait for either a replacement Shenzhou capsule to be launched or take over the Shenzhou 21 spacecraft, which arrived on the space station on Halloween with a new station crew. The problem is, that would leave the new crew without an escape mechanism if something else goes wrong. Apparently, Beijing does keep a space Shenzhou on standby for emergencies, but as to how long it would take to get that prepared for a space flight and have a rocket ready to launch it on is yet to be explained. The Shenzhou 20 crew arrived on station on April the 24th. Like the Russian Soyuz spacecraft on which it was originally based, the Shenzhou is composed of three detachable sections: a power and propulsion service module, crew living quarters, and a re-entry and landing module which is fitted with parachutes for the return to Earth. If any of these modules are deemed unsafe due to impact damage, mission managers would elect to deorbit the Shenzhou unmanned. It's not the first time China's Tiangong space station has been impacted by space junk. Back in 2023, one of the orbiting outpost's solar panels was hit, triggering a partial power shortage on station. China has since installed additional shielding to sections of the space station's exterior following that event. This is SpaceTime. Still to come, the biggest supermoon of the year, and later in the science report, a new study warns that up to 59% of Antarctic ice shelves are at risk of disappearing by the year 2300. All that and more still to come on SpaceTime. Skywatchers around the world have enjoyed a spectacular perigee full moon. The biggest so-called supermoon of the year appeared to be 7% larger and 30% brighter than the average full moon. This dazzling lunar show happened because the moon's orbit around the Earth isn't circular but elliptical. The moon orbits the Earth in 29.5 days, what's known as a synodic month. The moon cycles from a new moon to full moon and back again, always keeping the same face turned towards the Earth. The lunar orbit ranges from an apogee, the moon's most distant orbital position from Earth, of 405,000 kilometres, down to a perigee, its nearest orbital position to the Earth, of 356,000 kilometres. And this latest perigee moon was 30,000 kilometres closer to Earth than the average Earth-Moon distance. And so, when perigee occurs during a full moon, our lunar neighbour appears to be bigger and brighter than usual. Now, in reality, you probably wouldn't have noticed the difference unless it was pointed out to you. And just to burst another bubble, these so-called supermoons really aren't all that uncommon. In fact, there were 8 this year, 5 new moons earlier in the year, and 3 full moons at its end, the first back on October the 7th, then the just-occurred November 5th event, and another next month on the 5th of December. And another supermoon, that's a perigee full moon, will take place in January. One major effect of perigee moons is their impact on Earth's tides. When the moon is closer to Earth, its gravitational pull is slightly stronger, producing perigee and spring tides, which are a few centimetres higher than normal, a modest but measurable effect. As for the name supermoon, well, that dates back to the 1970s, and it wasn't invented by an astronomer, but an astrologer promoting his fantasies. Still, NASA thought it was catchy and adopted it to try and get more people interested in astronomy. The good news is, it worked. This is Space Time. And time now to take a brief look at some of the other stories making news in science this week with a science report. New research has shown for the first time that Australian marsupials are highly contaminated with synthetic forever chemicals, which have already been linked to significant health impacts in humans and other animals. A report in the journal Science of the Total Environment measured the concentrations of man-made per- and polyfluoroalkali substances in possums from the Greater Melbourne region. They found that all the possums they examined had been exposed to these forever chemicals with 45 different types in their livers. In fact, the problem's so bad, the average levels were among the highest ever recorded for any small terrestrial mammal anywhere in the world. A new study warns that ageing populations across Europe are set to fuel increased rates of antibiotic-resistant bloodstream infections over the coming decades. The findings, reported in the journal PLOS Medicine, used data from more than 12 million surveillance blood tests across Europe to track the changing rates of 8 drug-resistant bacteria from 2015 to 2019. They used that data to project future rates, with the rate of spread different depending on age, sex and country. The authors say drug-resistant infections are projected to increase more in men than women in the coming decades. And it will also increase dramatically among those over the age of 74, while stabilising or even declining in younger people. A new study warns that the world's carbon emissions remain high, with up to 59% of Antarctic ice shelves at risk of disappearing by the year 2300. The findings, reported in the journal Nature, claim existing predictions of how much warming the ice shelves can take focuses on the temperature of the atmosphere without fully factoring in the impact of warmer ocean temperatures. Simulating the structural integrity of 64 Antarctic ice shelves under the atmosphere and ocean warming of different emission scenarios, the authors found that only one ice shelf remained non-viable if warming is kept to below 2 degrees Celsius by the year 2300. However, if emissions remained high and warming escalated to 12 degrees Celsius above pre-industrial levels, 38 of the ice shelves studied in Antarctica will collapse, contributing to 10 metres of additional sea level rise. For all those Finding Bigfoot fans out there, there's a new story doing the news rounds apparently showing what's supposed to be a Sasquatch going for an afternoon jog. Tim Mendham from Australian Skeptics says a mysterious figure was captured on video jogging in the Sierra Nevada mountains of California. And of course, that means it must have been a Sasquatch. And who doesn't like a good Sasquatch story?
Who doesn't like a good Sasquatch story? Everyone does. Yeah, I love them. Loch Ness Monsters, Yowies in Australia, all these things. They're fun. They're the fun part of it.
You want them to be real, but you know they're not.
I love them to be. I mean, it's to be so dramatic and romantic and all this sort of stuff. But unfortunately, the evidence is not good. And its recent case was probably one of the least good bits of evidence. A video was released, filmed by someone named Bill, who has had filmed something in May in Coyote Ridge, California, a bit south of where you normally get your Bigfoot sightings and things, but that's okay. And he was watching his dogs playing in the snow or something like that, filming them, and suddenly there was this shape in the distance between the trees or behind the tree for about a second and a half. And if you look at the video, which you can do online...
He was jogging.
He was jogging. Now, either Bigfoot, Sasquatch jogging, or it was someone jogging.
We've never seen footage before of Bigfoot jogging. They usually come out at night rather than daytime, but jogging in the middle of the day, that's...
I've seen them ambling, but I wouldn't call that... Well, I've seen them in videos ambling, and they tend to think, well, it's a fake.
Well, they're still only dark shadows, aren't they? They're still only dark figures on the distance.
Normally, in forests and that sort of thing, you don't get a very good view, and it's always hazy. This one's not too bad as far as focus goes.
They're usually called squatch blobs.
Are they?
Yeah.
Right,
yeah.
because they're just a shape.
Exactly.
Yes, yeah. I mean, with this one, I mean, you can see someone moving through the trees. You don't get
no real determination of scale or...
No. And with the speed and the movement looks like jogging, and I would suggest gee whiz, maybe it's someone out there having a jog in Coyote Ridge, California. You can't really see the shape properly. You can't really get an idea of what it is. It's certainly human-like. Yeah, not the best bit of evidence, not the worst bit of evidence, I should add, but certainly not the best. And basically, like all evidence of Bigfoot, Sasquatch, Loch Ness Monsters, you name it, not very convincing, unfortunately. Unfortunately, I'd love it to be true, but so far, deep sigh, no.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.